Sure, it's the physics video lecture, psci 168, video lecture 22. We're in the middle of thermal physics, but I'm going to start off with some announcements. Namely, there's an exam coming up on October 14th. So, a bit ahead of the game, but that's good. October 14th, during class time. And you guys will I'll send you, say 15 minutes early, I'll send you a page of questions in email, and then within 15 minutes after class, you guys will send me your pictures as clear as you can make them to my email account. Don't send anything to Canvas, so do not send to, so send to my email. A couple people have been using Canvas. I'm not really in there, okay? So my email, most everybody's been doing, but this is for the record. CSU.Fresno.edu, right? Your name, psci 168 exam. I'm going to repeat this announcement anyway the next couple of hours, but that's how it's going to be done. And I'll even give a little review right now of the topics. It's going to be great. You don't have to worry about it, but we've covered so much stuff. Should be interesting. So let's see. That's what. Yeah. So as far as our review, which I will discuss more than once, but as far as the topics, there are topics where we do a calculation, and there are topics where we more just write some, long answer question, long answer form. But we're just going to go take it through the order that we studied them. So shape and size of Earth, that's a nice geometry problem. You guys will remember we had this construction, right, with the parallel lines and so forth. Then we would also have satellite orbits. I'll just write satellites, and just to remind you, the construction there goes with that Pythagorean theorem. That's a little crude, but you remember what we did, right? For the speed of the orbiting satellite. So we can say satellites and free fall. Then we have forces and triangles. So these are problems where I can assign some calculations and stuff like that. Then we have force, work, energy, power, just their definitions and examples. Then we have this very major topic of hydropower. And, we have the cartoon and the various formulas, of which there's really this formula primarily. Okay. Hydropower. See, if I number these, we're already 4, 5. And then we've gone into thermal physics. I'll give you more of a heads up later on that. So we have thermal physics, and we've made it all the way to the mechanical equivalent of heat, which is what I'm going to talk about today. Which is what I'm going to continue with, talk about some other stuff too. So mechanical equivalent of heat ties many, many things together. So yeah, you've got roughly an hour, a little more, to do the exam, write them all out, carefully as you can, take really good pictures, send them to my email account, and I'll see what I can do with it. Okay. So it should be great. Should be great. I'll give more information. Do you have any questions? Write to me in the emails as well. But those are the basic topics. And if you're not as mathematically inclined, you can always answer the question by starting out with the picture and a description of what you remember about it. But some of these problems I'll actually end up, with a calculation and a number. But again, if you just give that overview and outline of it, you get credit. I give a lot of partial credit on these kinds of things. And we take them in order, so we're trying to the way the whole subject is unfolding is the way that should unfold on your exam. Okay, what can you do in an hour? You fill a few pages and you're done. Good. So much for that, and we'll talk about it some more. It's all going to go to my email as before. So where are we in thermal physics? I'll get our little list going again. And then we'll do some really interesting examples with the mechanical equivalent of heat. So, hot and cold, once again, hot, cold. This time I'll write it really quickly. Hot and cold, we have those sensations. Then we have thermal expansion as a key phenomenon. And from thermal expansion, we have thermometers. Okay. And temperature scales. So the point here is that we haven't made contact with energy yet, as we learned about energy earlier. Right? Capacity to do work. Okay. So we had a couple of things. We've now learned thermal energy, the calorie. So this is where I'll pick up again. Calorie. And did I write it with a capital C or a lowercase? A little ambiguous. Let's go ahead and use the capital C. Lowercase is 1/1000th of one of these. And the cartoon that goes with the calorie is that we have on a stand with a candle underneath, water inside, and a thermometer. So that's the cartoon that goes with our calorie discussion. Because whatever we can do to raise the temperature of a liter of water by 1 degree Celsius, or a half a liter of water by 2 degrees Celsius, okay, whatever we can affect that change with represents a calorie. Okay. So calorie, raise the temperature of 1 kilogram of water by 1 degree Celsius. By 1 degree Celsius. And from there, we then had heats of combustion. First, we had them in terms of calories. So heat of combustion of fat, fuel, other fuels, alcohol, protein, carbohydrates, wood, coal, what have you. It's how many calories you get out of a certain amount of that substance. So there it was calories per gram, and we're going to look up a table of those, or give them more exactly. I wrote 9 for fat, 4 for protein, and so forth. Okay. So we have those heats of combustion, certain number of calories per gram. But then, right, and you can calculate however many calories you get out of a certain substance. For example, how many calories out of a pound of butter? Well, a pound of butter apparently had 3,200 calories, so you can then figure out the calories per gram for butter, for instance, by doing the conversion. Okay, but yeah, those are just constants. You can leave more or less room in your notes if you want to fill those in with some more examples. The next thing, though, was the mechanical equivalent of heat. So this I'm going to go through at length. I have some interesting examples for that. The mechanical equivalent of heat. And what we there do is do work. We do work, and via friction, we produce heat. So the work can be quantified. Work produces heat. Via friction, the work can be very carefully quantified. So we know exactly how many joules of work that we did, and then we know exactly how many calories resulted from those joules of work via the friction. So that was the joule churn we talked about last time. And what we find is that 1 calorie equals 4,186 joules. So I'm going to go ahead and write that up, and we'll do some interesting examples of that now. Yeah, so this is where we had arrived last time. Mechanical equivalent of heat. And as I recall also telling you that we have this direction from work into heat via friction. Eventually we're going to get the direction heat into useful work, okay? But that's going to require some more knowledge. So we're working on that direction, but we have this equation: 1 calorie equals 4,186 joules. And this here represents the whole thermal physics side. Okay. So this is the thermal physics. All that it took to come at the, to arrive at the definition of the calorie. We needed all that stuff on the list I just had on the board in order to really come to the definition of calorie and have thermometers and all that stuff. Okay. This here is mechanical energy up until now. Now the equal sign means that they're equivalent, but right now it's mechanical energy. And we know that mechanical energy is either potential energy or kinetic energy or both. Okay? That's what mechanical energy means. For example, in gravity, mgh, in kinetic energy, a half mv squared. So for example, mgh or 1/2 mv squared, all right here, etc. Okay, so there's our mechanical equivalent of heat. I like to ask on an exam, what is mechanical equivalent of heat? And it's a good start just to write this down, but then there's a lot that you can fill in with to really show the understanding, right? Because this is just the culmination of all of this knowledge down here. So here are 2 examples that I'll start with you, and you guys can complete them and leave room in your notes and turn them in as part of your homework. First one is a waterfall. So we have water flowing very slowly here down a stream. It comes to a cliff and it goes down the waterfall here, okay? And then at the base, of course, it collides here, and then it runs away slowly again. Okay, so it's in free fall here. Freely falling water, except there's enough friction, it doesn't just keep accelerating. At some point it drifts down, but it's really moving. And we have kinetic energy here. You can say we have potential energy up here. And of course, we're just going to say the height of the waterfall is h. So we're going to talk about the mechanical equivalent of heat in terms of this waterfall. So we have potential energy equals mgh, okay? Because here's our zero level. And then that gets converted into kinetic energy. But if you think that the stream had the same speed up here as it does down here, then that change in potential energy must result in something. And we could say, well, the water must be heated up. Okay. So when it gets dashed and smashed at the bottom of the waterfall, it will be warmed up a bit. And that's an interesting idea. And we can write it down this way. We can say mgh is equal to m times c times delta t. Remember, this was our last formula, basically, that we arrived at. In fact, I should have had it up here on my, since I have room here, you guys have room in your notes too. So mechanical equivalent of heat. After the mechanical equivalent of heat, we were able to define the specific heat, capacity, and then we said Q is equal to mc delta T. And part of the homework was to get a table of these specific heat capacities. Okay, so now that I remember that, I can make this a little more complete, like that. So start with the potential energy, convert to kinetic energy, crashes down on the rocks, and turns to heat Q. So now I've filled in these things, and you'll notice the mass cancels from both sides, and we want to solve for delta T. Solve for delta T, which I'll do here. Hope everybody's getting good at this. It's just such a common move, just an algebraic move. Delta T here, apparently we divide both sides by C. So we have G times H divided by C. You'll notice it's very important that all of our units are kilograms, meters, seconds, as I discussed the other day. And in this case, 9.8 meters per second squared, certain number of meters, specific heat of water. So C is of water. And here's what we'll do. I will put as an example, you guys look it up and calculate it. Actually, this one we'll probably do together right here on the spot. But since I don't have a calculator, you guys may want to plug in the actual numbers and get it exact. So our example, suppose we have a waterfall that's 200 meters high. Bridledale Falls up in Yosemite Valley is about 200 meters high. 700 feet, 200 meters. So we have H equals 200 meters. We want to ask, what is the change in temperature of water if all of that energy is just converted to thermal energy, to heat? So delta T is equal to GH over C. So we have 9.8 meters per second squared, 200 meters, and 4,186 joules per kilogram, joules per kilogram degrees Celsius. myself where this extra, oh, okay, the joules unit contains kilograms, so there's no problem there. Joules in parentheses equals kilograms meters squared per second squared. The units come out as degrees Celsius, as they have to. But you know, we can even estimate this. We've got 10 times 200, that's about 2,000 divided by 4,000. Well, we didn't need a calculator for this. It's approximately 0.5 degrees Celsius. Half a degree Celsius, 1 degree Fahrenheit. Not much, okay? That's interesting. It just goes to show there's a lot of energy in thermal energy, okay? Because a 200-foot waterfall, that's nothing to scorn, right? That's a lot of potential energy, mechanically speaking. In terms of thermal energy, you know, in terms of change of temperature, half a degree Celsius. Okay, so I did that one for you, but it's a good example. Let's do another example. So this time I just converted potential energy to thermal energy. This is maybe even a more realistic example. So this example here is, suppose we fire a bullet which is made of lead at some steel plate, okay? So we have a bullet, and the bullet is zooming along here. We can make up a number, but several hundred meters per second, you know, faster than the speed of sound. Okay. Go faster than that. Bullet hits steel plate. Okay. Boom. So it definitely comes to a stop. Okay. Big steel plate, bullet comes to a stop. And here we have 1/2 mv squared. So bullet hits steel plate. Kinetic energy is converted to heat. So there's our symbolic equation. Kinetic energy is converted to heat. So in that case, again, mc delta T. So what we want to do is calculate delta T, and this time I don't know the numbers off the top of my head, so I'm going to give that as a homework. And as usual, we just want it to fit in our notes, so leave some space. Homework, calculate delta T, and the question then is that enough temperature change to melt the lead? Okay. Does the lead bullet melt? Question mark. So we'll continue working right under here. Does the lead bullet melt? So yeah, I'll set this up again. It's really the same type of thing as we had right here. So solve for delta T. Solve for delta T, and again, as before, change in temperature in degrees Celsius. Actually, it's not quite as before. We're using potential energy. This time we have a 1/2 mv squared. So we have delta T equals mv squared over 2 times c. Not so fast. Masses cancel from both sides. So delta T is v squared over 2c. V squared divided by 2 times c. Let V is be equal to to make up a speeding bullet speed. I think 400 meters per second is legitimate. 400 meters per second. Some of you guys probably know more about the speeds of bullets than I do, but I think 400 meters per second is legitimate. And C is equal to the specific heat of lead. So you have to find the specific heat of lead, and then you've got V squared over 2C. Okay, so now the question is, does the lead bullet melt? So find also, you have to look up the melting temperature of lead. Melting temperature of lead, which is not that hot. I know you can melt lead in a, in a stainless steel spoon if you have a candle even, so it doesn't take much more than a candle flame to melt lead. And yeah, then you can compare that melting temperature to this change of temperature that you've calculated and see what you see. So yes, C is the specific heat of lead, not water. Water is vastly greater than the specific heat of lead, which is very low. So you have to find that. And so this is an example of kinetic energy being converted to heat. This one was, the waterfall was potential energy to kinetic energy to heat. So you see again, we had to have the kinetic energy concept and the potential energy concept to really discuss energy, because here we have these transformations that are pretty interesting. Let me give you a reminder. We had talked about the asteroid. So I'm just going to write here, recall our asteroid collision. There we had V was actually equal to, and we took it as an approximation. So I'll just write, V was on the order of 10,000 meters per second. Right? So a bullet pretty fast at 400 meters per second. An asteroid is a whole lot faster, 10,000 meters per second. And so you can imagine the asteroid explodes, releases a lot of heat. Who knows? Parts of it may melt. All kinds of stuff can happen to the asteroid. Okay, so that really is a nice part of the transformation of energy. Check for the time right now. Excellent. Okay. Waterfall, we've got the bullet. These are all transformations of mechanical energy into heat, just so you remember what we were doing here. Okay. Okay, so on our way through thermal physics, right, we're doing a lot of technical stuff. So I'm going to give you quite a bit more technical knowledge, but we don't want to lose the big picture. And so regardless of how technical it gets, we'll always return back to the big picture and the overall picture so that you can just remember a few cartoons and slogans about what energy is. For example, the capacity to do work. We're able to keep in our mind the entire picture of energy just by having the hydropower example in front of us. So we're going to do similar things for thermal physics, but right now we're picking up technical details. And our next topic is heat transfer, how heat gets from one place to another. It's not as though you're always firing a bullet at a steel plate, although that, you know, to go back to that bullet, when that bullet hits a steel plate, it does get very hot. It's lead, it can melt. And so you've generated heat there automatically out of mechanical energy. But heat can transfer in a number of ways. So we have to go deeper into that topic. But right from the outset, I want to go into discussion of something called entropy. So that's actually a very abstract technical topic, but we're going to make sense of it. We're going to need it later on. Again, without worrying about losing sight of the big picture. So heat transfer mechanisms and entropy. Good to have heard of this stuff anyway. So when we talk about heat transfer, we're just talking about how does energy get from one place to another. And what we learn by observation, heat flows from a higher temperature region to a lower temperature. From a region of higher temperature to a region of lower temperature. When you have spontaneous heat flow, that's what always happens. And the opposite does not happen. Now, it's going to take a little while, but we'll understand why refrigerator works, where refrigerator seems to violate this. But for example, if you have a hot cup of water here, and you put a spoon in, so you got a spoon in a hot glass of coffee or what have you, then the handle of the spoon is eventually going to be hot to the touch. Okay, so the heat actually flowed somehow. Spoon was initially cold, you put it in the hot water, and eventually the end of the spoon got hot. So that's called heat transfer by conduction. So, example, spoon in a cup of, how about a bowl of soup? Take your pick. Cup of hot liquid. Okay, the end of the spoon gets hot. So that's called heat transfer by conduction. Conduction. Eventually I have a few good demonstrations of this. Today we're just discussing the definitions. Okay, so heat transfer by conduction. So that was an example of this general law here. And what we do for our cartoon is we say, here's the law. If there's a hot object and a colder object, and you bring them into contact one way or the other with each other, then I have an arrow here, and the heat is going from the higher to the lower temperature. So this is our cartoon. I'll draw this 100 times in the course of the semester. And we'll know what we mean by this. For example, if this is a hot block of metal and this is a chunk of ice, and I bring them into contact with each other, the heat flows into the ice, we say, and it actually melts the ice and turns it into water. So this law you have to recognize that this is the direction the heat goes. And in other words, this is the direction that energy is transferred. Because heat flow is an energy transfer. Heat flow So we could say thermal energy transfer. Transfer of thermal energy. So what we're going to do next is bring that into contact with the atomistic idea. Let's check the time again. Yeah. So we're going to talk about what's going on at the atomic level, to the molecular level. So the same idea with the spoon and the hot fluid. I'll do a different version of it. So this version is like so. Suppose we have a flame. Ever since we made a butter candle, we can represent our flame by the butter candle. Okay. So we have a flame, thermal energy, heat and combustion, what have you, and we have a wire. I'm going to draw this wire as being pretty large and thick. So there's our flame. This is a metal wire. Could be copper, could be something else. But the same thing holds true. I'm applying heat right here. Okay. And if I grab this end, eventually this end is going to get hot. So the thermal energy is going to travel from the hot end to the cold end, and eventually this end will be warm as well. Okay. So the thermal energy travels from hot to cold, as in here, pH, Q, Tc. So this is an example of that. And the question is, what's actually going on in here? This is why we need the concept of atomism. What's happening actually is that the atoms in here are moving faster. As this heats up, the atoms are moving faster at this end and they're slower at this end. So the faster moving atoms collide with the slower ones, and the slower ones pick up some of that speed. And eventually, you could say these have kicked those to the right, and they've kicked all their neighbors until over at the end here, they're also being agitated. Okay. So we have faster molecular motion. I use the words molecules and atoms interchangeably, okay? Faster molecular motion. And that is transferred by collisions over to the slower side. So we have collisions. And this is all happening on the molecular and atomic scale. You can't see that. If you grab this, you just feel that it's warmer. Okay? Warmer over here than it is here. Eventually the heat makes its way in this direction. So yeah, this picture and this picture here are the same thing. This is the abstract version. This is the concrete version. But it's happening by molecular collisions. So we say heat transfer by molecular collisions, and is referred to as conduction. So molecular collisions. Okay. Conduction. And again, heat transfer, here you could say that the air molecules are moving very fast, and they're colliding with the wire, and they're also transferring by collisions, and then inside the wire, the collisions are transferring the heat all the way over to here. So this is important. Faster molecular motion corresponds to higher temperature. Higher temperature. We know it for the ideal gas. It's also true for the molecules inside a solid. So yeah, this deserves to be underlined and boxed in. So that's how one form of heat transfer occurs. But there's another aspect under which we can view this same thing here, and that has to do with order versus disorder. Okay. So over here where the molecules are slower, in fact this thing could be dipped in ice and they would be very slow. Where the molecules are slower with less random motion, we say they're more orderly. And where they're more rapid with more random motion, they're less orderly. Okay. So we can talk about the temperature and the speeds. We can also talk about the order and the disorder. Okay. So we have, if we're talking about temperature, we have high versus low speeds. And if we talk about what's called entropy, we're talking about disorder versus order. Okay. And what we're going to see is there are equivalent ways, these can be seen as equivalent ways to talk about something. Not quite equivalent though, there's an extra twist right here. So that's my first mention of what this entropy concept is going to entail. I'm going to leave it right here for now. So next time we really do have a bit of a technical discussion, but you know, we can always bring it back to these understanding of these examples. So until then, as far as homework goes, we just had those calculations with the change in temperature. You have to look up the melting temperature of lead and a few things like that. That'll be interesting. And other than that, you know, just keep up the good notes, and we'll see you next time.